Hi everyone, welcome to Power Electronics session 14. So far we discussed about single phase VSI. Now we are going to discuss about three phase inverters. In case of three phase inverters, we have two configurations. One is 120-degree mode VSI, other one is 120-degree mode VSI. The main difference between these two is only conduction angle of the thyristor. Circuit diagram is same, operation will be same, but the way we actually get the output is based on the conduction of each thyristor. In subsequent sections we will discuss like why we need to go for 120-degree mode VSI, whereas in 180 degrees is actually sufficient to supply the power and all. We'll discuss that. First we will discuss 180-degree mode inverter. In this case, or even in case of 120-degree mode inverter also, we will use the same circuit. Circuit wise no difference, only operation. That means how we will operate the number of thyristors in each case is different. We'll see that. Here in this like a three-phase inverter, we will use 6 thyristors and 6 diodes. As we discussed in single-phase system, each and every thyristor should have anti-parallel diode to have the reverse power flow when you have inductor in load or reactive element in the load. That is required. Otherwise, you can't operate the thyristor, you can't operate inverter. Okay, so for simplicity, we are going to discuss with the help of resistive load only. Why we need to go with only resistive load means we already concluded in single phase system output voltage waveform will not depend on the type of the load, only current waveform will be different, but we are not going to discuss about the current waveform. Mainly we are focusing on the output voltage waveform. So in that case it doesn't matter what load we connected to the inverter. That's why for simplicity or easy we are going for resistive load. And this capacitor potential divider is not required, but we are discussing this one to answer one of the gate question. That's why this is not mandatory here. So here we will have 3 legs. First leg we will have like thyristor T1 and T4. Second leg will have T3 and T6. Third leg will have T5 and T2. Each leg is connected to one phase, and this load configuration is actually we are discussing with the star connection for easy way, but we will conclude that what will happen if the delta connection is there. And there are some questions in gate exam with respect to delta connection, but no need to discuss separately with the delta connection. Once we know things about star connection, we can actually conclude that what are the necessary changes will be there in delta connection. Okay, so in case of 180-degree mode inverter, we will operate these thyristors in 6 combinations. Each combination is actually having 3 thyristors, okay, 1 from each leg. And we will make sure that in these combinations, no 2 thyristors from the same leg. In case if you have 2 thyristors from same leg, means it is short circuiting the source. If source is short circuited, then obviously thyristors will be damaged because they carry huge amount of current. So that's why you can see here we are going to operate these thyristors in these combinations, like 6 combinations. Each combination is actually having 3 thyristors, 1 from each leg. Another thing is also we will not operate the thyristors from the combination with the help of combinations, and those combinations will not have all 3 thyristors from the lower bank of thyristors or upper bank of thyristors. Generally we will have lower bank of thyristors or upper bank of thyristors to have the 0 voltage only, but we are not going to discuss that. Okay, we are actually using 6 steps only. That's why it is also called as a 6-step inverter. So here each combination is meant for 60 degrees. That means T by 6 seconds. T is nothing but time period of the output voltage. So this is actually 60 will be in conduction for 60 degrees. This will also be in 60 degrees. This will also be in 60 degrees, and so on. If you go for that means So it will cover total 360 degrees. That means to get one output cycle, we need to have all 6 combinations. That's why you can see that each combination will be in conduction for t by 6 seconds. That's why we will cover one time period. That means 60 degrees each, nothing but 360 degrees. And now you can see here, first 3 combinations, T1 is common. That means if you look at that T1 conduction, it is in 3 combinations, means 60, 60, 60, that means 180 degrees. So this is not only with respect to T1, it will be with respect to the T2. You can see that T2 is in 3 combinations, T3 is in combination, T4 is in 3 combinations, like that. That means each and every thyristor will be in conduction for 180 degrees. That is why the name of this inverter will be 180 degree mode. So that's the meaning of that. Okay. So based on the conduction of each thyristor only, this is called as a 180 degree mode inverter. Okay. We'll discuss about how this inverter will be operated and all. We'll see. So here we can see that we will take 1-1-1 combination, how this inverter will be operated, and how the output will be there, and all we will discuss. First combination is T5, T6, T1. If I turn on T5, T6, T1, that means T1 from upper bank of the first leg, T5 is from upper bank of the third leg, and T6 is from lower bank of the lower bank of the thyristors. Now if I consider only the first combination T5, T6, T1, and respect to thyristors I shown here, and remaining diodes and thyristors I removed from the circuit. You can see that here for simplicity I told you that we are going for resistive load to draw the load voltage. In that case, no need to worry about the diodes, because diodes will not be in conduction for resistive load. That is why I am just removing all these things from the circuit diagram. Now we are actually having T1, T6, T5. So if you turn on these thyristors using the gate voltage, then this will be in conduction. That means acting as a short circuit. This will be acting as a short circuit, and this will be acting as a short circuit. Now look at that. Phase A is connected to positive terminal of the source, phase B is connected to negative terminal of the source, and phase C is connected to positive terminal of the source. So that's the meaning of that. So now how how the voltage will be appear across each phase we need to discuss. If you look at further, if you eliminate everything and then just look at only the respective thyristors T1, T5, T6, you can see these phases are connected to the source voltage like this. Forget about this for some time, no need to worry this one. Now if I'm actually looking at this way, like a circuit diagram, how this will be connected and all, if I'm supplying the power from this, nothing but current is supplied by this one and coming to this place. Till this point it is actually source total current will be there, but here it is splitting into 2 portions, nothing but these 2 branches are connected in parallel. So that means phase A and phase C are connected in parallel, and then the respective currents again meeting here at the neutral point and flowing through this one. That means this parallel combination is in series with the phase B and then returning to the source current. That means this, if you are taking the equivalent circuit, it will be like this. As I told you that phase A and phase C are connected in parallel, phase B is in series with the parallel combination. That's the meaning of that. This is a simplified circuit diagram. From this we will discuss that what will be the voltage across each phase. Okay, now if you look at here, the same thing what I shown that in the previous phase, same we are taking that equivalent circuit. Now we are actually calculating what will be the voltage across each phase. Look at here, this is a balanced load. So in case of 3-phase system, balanced load is there means per phase resistance will be same. That means RA, RB, RC equal to the R. So if you consider that means R and R are in parallel, then you will get R by 2. So this combination in equivalent is R by 2 and this is R. So this R by 2 and R are connected in series to the same source voltage, then based on the voltage division formula, you can see that less voltage will be appear here and more voltage will be appear here. So that means three portions will be there. One portion will be appear here, 1/3 portion, and 2/3 portion will be appear here. Sorry for the mistake here. Okay, so voltage across the RB will be 2 VDC by 3, and across phase A and phase B will be VDC by 3. So now if you consider the neutral point, because neutral point will be there here, okay, here neutral point will be there. With respect to neutral point, these phases are connected to positive terminal of the source, that's why this will be positive VDC by 3. And with respect to neutral point, this phase is connected to negative terminal of the source, that's why this is minus 2 VDC by 3. Okay, another important thing we need to remember from the three-phase system, once you got the phase A voltages, if the load is balanced load, then sum of the phase voltages, okay, sum of the phase voltages will be 0. That means you can look at here, phase A voltage is VDC by 3 and phase B voltage is minus 2 VDC by 3. Phase C voltage is VDC by 3 because phase A and phase C are in parallel. Now sum of these three voltages will be equal to 0. That means it is indicating the balanced load. Okay, so that's what, based on this, with respect to neutral point, this is positive, this is negative. Now here we are going to draw 4 voltage waveforms. One is, that is like if you look at the circuit diagram again, one voltage is like we will draw, that is called pole voltage. Pole voltage is nothing but voltage difference between the middle point of the leg and the center point of the capacitor divisor. So capacitor potential divider. So that means pole voltage A. That means VAO. So that is nothing but difference between these two. Like that 4 voltage B between this one and this one, and 4 voltage C between C and O. As we know that balanced three-phase system means each and every phase voltage and line voltage will be 120 degrees apart. That's why we are not going to discuss each and every voltage waveform. Only one voltage waveform if it is sufficient, and if you want to know the remaining, we need to take the 120 degree phase shift. So likewise, we are going to discuss another voltage is nothing but phase voltage. So phase voltage is nothing but voltage difference between this one and neutral point. So this is the A and N is nothing but phase A voltage. Potential potential difference between this point and this point indicates the phase B voltage, like that phase C voltage. So we are going to discuss about other one is phase A and phase B. Why we need two phases? Because we need to calculate the third voltage, that is nothing but line voltage. So what's the line voltage? Here line voltage is nothing but it is the voltage difference between two phases. Between two phases is nothing but between A and B or B and C or C and A. So that's what like we are going to discuss. Only one line voltage, line AB, that is nothing but potential difference between two phases. That's nothing but VAN minus VBN. That's why we are going to discuss two phase voltages. Otherwise one phase voltage is sufficient. So that means we are going to discuss about the three different waveforms here. So if you look at here, three different waveforms means, first one, as I told you, that pole voltage VAO, second one is VAN, and other phase voltage VPN, and other and final voltage we want line AB voltage. Okay, so that's what we are going to discuss. If you want to know that what is the pole voltage, you can look at here. So pole voltage, we are taking the difference between A and O. if you're taking A and O means, you can see when this thyristor is in conduction, this is acting as a short circuit. The potential point at A and at this point are same because this is short circuit. This point and this point are same. So when you are measuring A and O, indirectly you are measuring O and this point. So the difference between this one and this one, you can see that VDC by 2, and A is connected to positive. That's why positive VDC by 2 will be the voltage for the pole A. So that is what we are going to draw now. If you are going to draw that pole A voltage means for the first combination, that means I'm talking about first combination 1. In this combination 1, pole A voltage will be VDC by 2. Okay, likewise, phase A voltage we already discussed, VDC by 3. Phase B voltage we discussed, there is a 2 VDC by 3 minus, that means negative 2 VDC by 3. And as I told you that line AB voltage is nothing but potential difference between these two phases. That means VDC by 3 minus of minus 2 VDC by 3. That means it will give you VDC. So that is the line voltage for this particular combination. Likewise, we will discuss about other combinations and we will conclude what will be the voltage and voltage waveform for phase and line voltage in case of star connection. Okay, so next combination is as we discussed already. First combination is done. Then we are talking about the second combination here. Second combination in this case is nothing but T6, T1, T2. That means the transition happening between T5 and T2, both are from the third leg. Okay, after 60 degrees, T5 will be turned off and we are turning on T2. Okay, that's the meaning of that. And remaining two thyristors will continue. So in this case, we are turning on, that means T1 is already turned on in the previous combination, that will be continued. T6 will also be continued, but now T5 will be turned off after 60 degrees and we will continue or turn on the T2 from the same leg. Okay, so now you can see that phase A alone connected to positive terminal of the source and phase B and phase C both together connected to negative terminal of the source. As we discussed in the previous combination, whichever the thyristors are actually connecting the respective phases to the positive terminal of the source, then the corresponding phase will get the positive voltage. Whichever the thyristors are connecting the respective phases to the negative terminal of the source, those phases will get the negative voltage. That is what we get earlier. That's what you can see there. Phase B is connected to negative terminal of the source through T6 and phase A connected to the positive terminal of the source through T1 and phase C is connected to the positive terminal of the source through thyristor T5. So that's why phase A and phase C got the positive terminal voltage, phase B got negative voltage. And another important thing we need to remember here is which of the phases are connected in parallel will get the less voltage. Which of the phases are connected alone, those phase will get like more voltage, 2 VDC by 3. These are the things we need to remember. Again, I'm telling that simple thing to get the equivalent voltages, whichever the phases are connected to positive terminal of the voltage, those will get positive voltage. Whichever the phases are connected to the negative terminal of the source, those will get negative voltage. And another important point is whichever the phases are actually connected in parallel, those phases will get lesser voltage, that's nothing but VDC by 3. Whichever the phase is connected alone to the source, nothing but in series with the parallel combination, that phase will get more voltage, that is nothing but 2 times VDC by 3. Okay, these are the two things we need to remember. Now we can see that second combination, phase A and phase C are connected together to the negative terminal. That means these two are parallel combination, and this parallel combination is in series with the positive phase A and connected to positive terminal of the source. That means this will get more voltage, these two phases will get less voltage and negative voltage. So Further, we will see that what will be the equivalent circuit. Same thing what we discussed, that is actually taken as an equivalent circuit like this. Now, as we discussed, phase B and phase C are connected in parallel and to the negative terminal of the source. Why negative terminal of the source? Because these two phases are connected to the source through the lower bank thyristors, nothing but T6 and T2 respectively. Okay, and phase A alone connected to the positive terminal source through the thyristor T1, that is the upper bank of the thyristors. Upper bank of the thyristors connects the respective phases to the positive terminal of the source. Lower bank thyristors will connect the respective phases to the negative terminal of the source. So that is what. Now, if you take the equivalent circuit with the source voltage, like the respective phase voltages, you will get like this. That means this is single phase connected to positive, so that's why you will get more voltage, 2 times VDC by 3. This will be this combination is in parallel, that means this will get less voltage VDC by 3. But as I told you that it is like a balanced load, and if you consider the neutral point here, then you will see with respect to neutral this will be positive voltage, with respect to neutral this combination will get negative voltage. Now you can see that simply phase A is actually having positive 2 VDC by 3, phase B and phase C are having minus VDC by 3. Again, if you take the sum of these phase voltages, you will get the 0. Now first combination we already discussed. Now we need to plot for second combination. Second combination, we just now taken the voltages, phase voltages. So phase A voltage is positive VDC by 3, positive 2 VDC by 3, and phase B voltage is minus VDC by 3. Okay, and line AB voltage is VAN minus VBN, so positive 2 VDC by 3 minus of minus plus VDC by 3, again it is VDC. But folio voltage remains same because still thyristor T1 is in conduction, so this potential point and this potential point are same, this and this are same. That means if we are measuring across, this means we are measuring across this one, that is a VDC by 2. So we will continue with same voltage in second combination also. Okay, so that's the meaning, so remember that. Next, moving on to the third combination. What is the third combination? Third combination is T1, T2, T3. That means if you look at here, third combination is T1, T2, T3. So if the third combination is T1, T2, T3 means T1 is common, T2 is common from the previous combination. Now the commutation is happening between T6 and T3, that is on the second leg. So here in this case, we are actually going for the combination T1, T2, T3 means T1 is actually in conduction from the previous combination, T2 will be in conduction from the previous combination. Now we are turning off the T6 and turning on the T3 from the same leg. So now transition is happening from phase A, from negative side of the lower bank thyristors to upper bank thyristors. Now you can see phase A and phase B both are connected to positive terminal of the source. That means these two are in parallel, and phase C is alone connected to the negative terminal of the source. That means this is actually getting the negative voltage, which is actually more than other two phases. So that's one. So if you simplify this circuit further, we will have like this. If you consider only those elements which are in conduction, then you will see that. If you further simplify this circuit, you will have this one. As I told you, phase A and phase B connected in parallel to the positive terminal of the source, and phase C alone connected to the negative terminal of the source. As we discussed in the previous combinations, these two will actually get lesser voltage, that is VDC by 3. This will get more voltage, 2 VDC by 3. But with respect to neutral point, this is negative, this is positive. The same thing we are discussing here. Okay, so that means as it is what we discussed in the previous one. So now if you consider the neutral point here, so Parallel combination will always have the lesser voltage VDC by 3, but it is positive because it is connected to positive end of the source. Single combination, that means single phase, will always get the more voltage 2 VDC by 3, but it is negative with respect to neutral. So that's one. So now in this case, phase A, phase B will get same voltage, phase C will get different voltage. So if you take that, this is the first combination, this is second combination, now third combination. Third combination, phase A voltage is positive VDC by 3 from this one, and phase B is also positive VDC by 3, and both are same means the difference will be 0. That's why line AB voltage will be 0 in this case. Okay, and still thyristor T1 is in conduction, that's why pole A voltage will be same as earlier combinations. That's why here pole A voltage will VDC by 2. Okay, so now we completed the 3 combinations so far. Next we will move on to the 4th combination. Okay, so if you look at the 4th combination, what is the 4th combination? T2, T3, T4. Okay, T2, T3, T4. That's the 4th combination. So here T2 will be in conduction from previous combination. T3 will be in conduction from the previous combination. Now we are having the commutation on the first leg only. That means T1 actually completed its conduction 120 degrees by this time, and it is going to be turned off end of 180 degrees, and we are going to turn on the thyristor T4 from the first leg. That means so far phase A is actually got the positive off cycle. Now we are going to get the negative off cycle by thyristor T4. Okay, that's what. So if you simplify this one means, you can see here, so thyristor T4 connecting the phase A voltage to negative terminal of the source, T2 connects the phase C voltage to the negative terminal of the source. That's why phase A and phase C are connected in parallel to the negative terminal of the source. Only one upper bank thyristor is here. That's why phase B alone connected to the positive terminal of the source. That's why if you take the equivalent circuit of this one, you will have like this. As I told you, further equivalent circuit means phase A and phase C are connected in parallel, and that parallel combination is connected to negative terminal of the source. Likewise, phase B alone connected to the positive terminal of the source. So this is a combination. Now by looking at this combination, as we already discussed in the previous combinations, you can see that single phase will always get more voltage. That's nothing but 2 times VDC by 3. Parallel combination will get only lesser voltage, that is VDC by 3. But with respect to neutral point, these will get negative, this will get positive. Same thing is discussed in this one. Okay, so positive 2 VDC by 3 will be appear across phase B, negative VDC will be appear across phase A and phase C. Okay, we already considered the waveforms here. You can see that this is the combination 1, this is combination 2, this is combination 3, combination 4 already considered. Okay, so here phase A is getting minus VDC by 3. So far we got the positive off cycle, now negative off cycle for the phase A. Phase B is 2 VDC by 3 positive, that's why here resultant will be negative VDC for the line AB. And another important is now thyristor T4 is connected here. So okay, thyristor T4. So now thyristor T4 is in conduction means this potential point and this potential point are same. That's why if you are measuring potential difference between A and O, now we can see that this and this are same. This is A, you can say. So now this and this point are same means this is A. If you are measuring across AO, then you are measuring across AO. So this potential difference is VDC by 2. But now A is connected to negative terminal. That's why minus VDC by 2. That's why we are getting minus VDC by 2. So that's the 4th combination. Next, 5th combination. What's the 5th combination here? 5th combination is T3, T4, T5. Okay, T3, T4, T5. So in this case, T3 is common from the previous combination, T4 is common from the previous combination. Now commutation is happening between T2 and T5, which is on third leg. So T4 is in conduction from the previous combination, T3 is in conduction from the previous combination. Now we are going to turn off the T2 After its conducting angle by 180 degrees, then we will turn on the thyristor T5. Now look at that. Two upper band thyristors are there in conduction, means respective phases, phase B and phase C, are connected to positive terminal. Those are in parallel. Next, lower band thyristor, only one is there, that's why respective phase will connect to the negative terminal of the source. If you take the further equivalent circuit, look like this, and equivalent will be simple equivalent circuit like this. As we discussed, only one thyristor is there from the lower band, that's why phase A is connected to negative terminal of the source. Phase B and phase C are connected in parallel, and it is further connected to the positive terminal of the source. So as we discussed in the previous combinations, so voltage across the parallel combination is voltage across the parallel combination is VDC by 3, and with respect to neutral point, this is positive. And single phase is always getting more voltage, that's why 2 VDC by 3, and it is negative with respect to neutral. So that's we already taken care. So this is a combination 1, this is combination 2, this is a combination 3, this is 4, this is 5. Okay, in the fifth combination, T4 is still in conduction, that's why minus VDC by 2 we will have pole voltage, and negative voltage will be there, minus VDC by 3, that's what we are getting. Phase B voltage is positive VDC by 3, and difference between these two is VDC. And next and last combination to complete one output cycle is sixth combination. What is the sixth combination here? So sixth combination is nothing but we are having T4, T5, T6. So T4 is common from the previous one. T5 is continuing the conduction from the previous combination. Now the commutation is happening on the second leg between T3 and T6. So that means T4 will be continuing the conduction from the previous combination. T5 will be in conduction from the previous combination. Now at the end of 180 degrees of the conduction by thyristor T3, we will turn off the thyristor and turn on the T6 from the same leg. Now you can see that T4 and T6 are connecting the respective phases to the negative terminal of the source. That means these two phases are in parallel and will get the negative voltage, which is minus VDC by 3. And upper bank only one thyristor is there, that is a T5 connecting the phase C to the positive terminal of the source. That's why this phase will get the positive voltage, that is 2 times of the VDC by 3. Okay, if you take the equivalent circuit, this will be simple like this, as we discussed already. Now voltages, yes, phase C alone will get the single voltage 2 VDC by 3 positive, phase A and phase B will be minus VDC by 3, and T4 is still in conduction, that's why pole voltage will be minus VDC by 2. Okay, so as we discussed, this is a combination 1, combination 2, third combination, fourth combination, fifth combination, sixth combination. Now look at that, one cycle is completed by the phase A by having 6 combinations, like that phase B also. So the difference between these two is again 0. So likewise, so if you continue further, this one means we will have again combination 1, combination 2, then we will keep on getting the waveforms like this. Remember, so here a few things we need to remember. The first thing is pole voltage is perfect square wave. This is called 180 degree square wave mode. Okay, this is perfect square wave. Okay, this is also called 180 degree mode. Then phase voltages are actually having stepper square wave. Okay, these are stepper square waves. And line voltage, here we are taking only one line voltage, but line voltage is having quasi square wave. Okay, so line voltages are quasi square wave, phase voltages are stepper square waves, and pole voltage is perfect square wave. Okay, remember this. We'll again come back to this one. Okay, so we need to discuss here output voltage waveform, output voltage equations. Which one is easy to calculate the RMS voltage? Line voltage is easy or phase voltage is easy? Line voltage is easy or phase voltage is easy? By looking at here, if you take the phase voltage, means we can calculate the RMS value by using phasor line voltage. But you can see that here, if you consider half of the waveform, you have the 3 segments here. But here we have 3 segments. 2 segments. One is a square, other one is 0. So it is easy to calculate. So that's why we will consider the line voltage to calculate the output voltage. So here output voltage. So it is V0 RMS line. Okay. So that is equal to, as I think you all remember about that, how to calculate the RMS value from the waveform. That's what we discussed. So in the beginning of the class, this is segment 1, this is segment 2, and it is a kind of like a symmetrical waveform. That's why no need to consider the second half cycle. First half cycle is sufficient. So you can see that this wave is there for 120 degrees, okay, out of 180 degrees. Okay, you can consider that one. If you consider that one, as I told you that we need to take this root of, okay, so RMS value of the segment 1. RMS value of the segment 1 means segment 1 is nothing but square wave. Square wave RMS value is VDC. V is like maximum value. Maximum value you can take, that is nothing but VDC. VDC square multiplied with available duration of this waveform. Available duration of this waveform is 120. 120 is nothing but 2 pi by 3. Okay, 2 pi by 3 plus second segment. Second segment nothing is there, that's why 0. Leave it. Whole divided by time period. What is the time period here of this waveform? 180 degrees. That means pi. Okay, so pi gets cancelled. You will get VDC square into 2 by 3. So VDC square means you can take outside the root, that's nothing but VDC root of 2 by 3. Okay, so this is the RMS value of output voltage per line. Okay, likewise, but sometimes we need to have like a phase voltage only, because phase voltage will only give that power and then current, etc., like that. So in that case you can actually go for phase voltage. So phase voltage RMS value is, so what combination of the load we discussed so far? It is a star connection. In case of star connection, how to calculate the phase voltage? Phase voltage is nothing but line voltage divided by root 3. So line voltage divided by root 3 means VDC into 2 by root 3 divided by root 3. That means it will give you root 2 VDC by 3. Okay, so this is the phase voltage. Remember that. Okay, so that's one. And another important thing here we need to remember is Fourier series for this waveform. Okay, so it is simple to have the Fourier series for the line voltage. Once you have the line voltage, you can get the phase voltage as like a relation between phase and line. So that's why I am giving the Fourier series for this one for the line voltage. So it is line AB. Okay, as we discussed, for any square wave, it will be having only odd harmonics. N is 1, 2, 3, 5, infinity. Then 4 by n pi is common for any waveform multiplied with magnitude. Magnitude is VDC. So 4 VDC by n pi into, as we discussed in rectifier's case, if any cosinus is there, if you are representing the cosinus, then we need to use the cos. If you are representing the pulse width, we need to use the sine. Both will give you the same result. That's why I am actually using here cos n pi by 6. That's the cosinus into sine Okay, so this pi by 6 is actually because this waveform is not symmetrical about 90 degrees. If it is symmetrical about 90 degrees, then this pi by 6 will also not be there. Okay, that's what. So that's what. So remember, another important thing we already discussed in rectifiers. In place of this one, we can use the sine also. When you're using sine, we need to take the pulse width. Pulse width is 120 degrees. 120 degrees divided by 2, 60. So then you can use sine n pi by 3. That also can be used in place of cos. Okay, that's what. So remember, this is, so if you want to know the respective things from the Fourier series, from the respective things for the phase voltages, you can use the line voltage, and after that, once you calculated whatever the things required for the line, then divide with root 3, then you will get the phase voltages. That's why no need to worry about the phase voltage Fourier series. But remember here, why we discussed about the pole voltage is important here. Why we are actually discussing means, you can see here, if you substitute n equal to 3, so if you substitute n equal to 3, either this or this, both will give the same. Okay, no need to worry. If you directly substitute here n equal to 3, n 3 gets cancelled, sine pi. Sine pi is nothing but 0. Okay, or you can see that n equal to 3 means it is pi by 2, cos pi by 2 is 0. So if you substitute n equal to 3, 0, n equal to 9, then 9 by 3, that means 3, sine n pi, any multiples of 180 degrees in case of sine will be 0. That's why n is 9 means 3 pi 0, n is 15 0, n is 21 0, n is 27 0. What are these things? We discussed already in case of rectifiers. What is that? For quasi square wave, if the cosinus is 60 degrees, then obviously the harmonics present in that waveform is all odd harmonics except triplet harmonics. Triplet harmonics is 3 multiples. That is why in case of 3-phase system, even with the line voltage or phase voltage, in case of 3-phase system, you can see that here triplet harmonics will not be present. Triplet harmonics will not be present means first harmonic in case of 3-phase system is 5th harmonic. Okay, 5th harmonic will be the first harmonic, because n equal to 1 will not be the harmonic. That's why 3rd harmonic will not be there. So 5th harmonic. That means in case of phase waveforms or line waveforms, you will have all odd harmonics except triplet harmonics. Nothing but 3rd, 9th, 15th, 21st, these harmonics will not be there. Okay, remember that. So again, the pole voltage is proper square wave, perfect square wave. Perfect square wave means no cosinus. In this case, we will have all odd harmonics. All odd harmonics. Okay, because cosinus is not there. We discussed in the single phase rectifiers. In that case, n equal to 1, 3, 5, 7 and so on. That means 3rd harmonic, 5th harmonic, 7th harmonic, 9th harmonic, everything will be there. That means all odd harmonics will be there. That is the difference we need to remember. Okay, so moving on. So coming to the final conclusion of 180 degree mode means, okay, we will turn on all these thyristors for 180 degrees for complete conduction of each thyristor, and we will get the waveforms like this. Look at here, for the, if you're talking about the first leg, so that means phase A, after 180 degrees, what we are doing here? After 180 degrees, we are turning off the thyristor T1. Okay, we are turning off the thyristor T1 and immediately we are turning on the thyristor T4. So T1 generally connects the phase A to positive. So end of 180 degrees, we are completing the conduction by thyristor T1 and turning off that, and immediately we are turning on the thyristor T4. If you turn on the thyristor T4, we are getting negative voltage. Like that, and the phase B also. Phase B means here we are completing the conduction by thyristor T6 and we are turning on the thyristor T3. Okay, this also after 180 degrees again thyristor T3 will be turned off and T6 will be turned on. So that will be there on every phase for every 180 degrees conduction of the respective thyristors on that particular leg. So now here you can see, so here we turn off the thyristor T1 and immediately we are turning on thyristor T4. If everything is ideal, then thyristor T4 will be turned off once you start the commutation and T4 will turn on immediately. There will not be any problem. But generally, if it is a small delay is there, like turning off the thyristor T1, if it is taking little time and T4 is turned on, then both are in conduction, means you will have a short circuit. Okay, so that means if any two thyristor, that means any two thyristor from the same leg are in conduction for a short duration, then what will happen? Short circuit will happen. That's nothing but source short circuit. Source short circuit is happening means no resistance or no load in between. That's why huge amount of current will be flowing through the thyristors and those thyristors will be damaged. But in general, we will not have a separate thyristors T1, T2, P4, T5, T6 or separate diodes on like a chip. What will happen? We will manufacture or we will form all thyristors and diodes on a single chip only. So if one thyristor and one diode is damaged, means we need to replace entire this chip. That is a costly. That's why we will actually give the minimum duration between the transition from the thyristors from same leg to avoid the short circuit of the source to protect the thyristors. So here we will actually take care some delay from thyristor T1 to complete the turn off, and then we will turn on the thyristor T4. Likewise other thyristors also. That is why we will go for the 120-degree mode. So here there is a possibility of the source short circuit while changing the thyristors from one to another on the same leg. That's why we are going for 120-degree mode. But the problem is there with 120-degree mode. If the conduction of the thyristors are reduced, means power supplied to the load will also be reduced. But okay, power management we can take care with the help of any additional things and all, but mainly we need to protect the thyristors. That's why we will go for 120-degree mode, even though there is a problem with conduction. Okay, nothing but power conduction. Okay, we will discuss the remaining things in 120-degree mode. Okay, thank you, and we will discuss remaining things in the coming video.